So in the end, exactly. So in the end, what are we doing? Let me try to explain a little to you.
Sir, can
What
you
our
switch to the uh
does it work?
yeah, it's working, but can I get the full screen?
You don't have the full screen?
Yeah,
You only see the settings. Okay,
because
give me a
I
second.
still see in the presentation mode.
So, does it working now? Do you
At
see
the
now the full
bottom,
screen?
yeah, yeah. Can you just switch to the presentation mode?
This is
The last
presentation
button
mode.
there.
The last button there. Hmm. For me, it is in presentation mode.
Okay.
So let me see. Interesting that it's not for you.
Yeah. For me,
So
I can
is this
still
is this
see the other slides on the left panel.
okay?
Maybe
And
you stop
now
sharing and come back again, sir?
Uh, Nim,
maybe I can.
can you
Yeah.
just
Maybe I
put it
can
in the
do this.
slideshow? Can you
Yeah.
put it in slideshow,
Yes.
Nikolai? We can see your screen. We can see your PPT.
Ah,
Yes.
yeah. That's
Go ahead.
perfect.
Go ahead.
That's it. Okay.
Yeah.
Perfect. All right. Thanks a lot. So in the end, this is actually what we're doing. We're using, as you can see, lasers to actually project images for different applications. And as you can see, this is really, really small. So as you can see, this is really the hand of a human being holding our projection engine. And in the graphic below, actually, it's a little bit how this works. So in the we got three laser diodes, a red one, a green one, and a blue one. Uh, we do have some lenses then there, a lens system, and then we have a mirror there. And with this mirror, we can actually project onto a screen or onto into a waveguide, actually images that we want to have. And this actually means that we can use this kind of projection technology, which is called laser beam scanning, for many different applications. What you can see here in the picture right top is actually uh, the Drexel cube. It is 1 cubic centimeter, so it's nearly 1 by 1 by 1 centimeter of volume only, which is actually used for AR applications. What is AR? AR means augmented reality. So this is really can be used to put it in your AR classes in classes that you can use for many different applications. And there, of course, it makes a lot of sense to have it very small and very lightweight because you don't want to have something heavy on your glasses. On the other side, we're also using it for automotive application, and I will show you application examples later on that we use also this kind of sizes, but also a little bit larger sizes to project things on the ground, in the head-up display and that kind of stuff. So in the end, what we have here is a very nice piece of technology where actually we can use it for many different applications. Uh, we we have shifted a lot of the complexity that is actually associated with those kind of laser beam scanners into the software area. So in the end, this means that a lot of the uh, challenges and obstacles which need to be solved, starting from the design of the whole thing to the manufacturing, are actually solved in software. And of course, we have this in a lot of patents that we have actually done. And last but not least, we also recognized as the expert in this field. So we were known around the world for our very small projection displays. And let's move it on. Where is it used? So in the end, as you can see here, this is an application example. These are classes. And what you can see here is actually our Drexel, uh, how we call it, the Drexel device, the cube in a very small design form factor that you wouldn't even see it in the classes. And why can we do that? Because we have the smallest size out there. We are very lightweight, low power consumption, and we also have got a very high brightness and contrast. And of course, this all is enabled by laser technology, because only laser technology gives you these advantages there. And one other advantage is actually also the high color gamut. So you can display everything in full color RGB, which is really, really nice, because what you would like to have, you would not like only like to have something which is small size and very lightweight in your glasses, but you would also like to have something which is very has a very high picture quality in your glasses. Because if you only have a green only version or whatever, this is actually, especially if you plan to use it longer during your work days, for example, this is not very convenient. Why are we there? Just a quick, so this is actually where we are right now. So this is 2024, which is actually last year. So the market has been quite small, but it is developing. And what we see here, that until 2030, the market, and especially what we can look at into, is the consumer AR, which what I said means augmented reality. From the high end, also the entry level, this will grow tremendously. And especially in the high and mid end, this will really grow a lot. And this is why we are very well suited to serve these kind of applications, these kind of markets, with our very small form factor solution. But this is not only something that actually we are seeing. So this is why I also would like to share this picture with you. This actually is a representation from one of the key guys, of one of the pioneers, I would say, in laser technology, uh, which is actually Meta. And this Meta, actually, they really see LBS, so laser beam scanning, which is our technology, as one of the key technologies for the future. And again, there are other competing technologies out there, for example, LCOS, liquid crystalline silicon, and also micro LEDs. Both of them are still quite used quite heavily, but as you can see, they have certain limitations which will be very difficult for them to overcome. And we see us already at the stage where we have overcome all of the technology drawbacks that the other solutions have, and actually see already LBS in front. And this is one more time uh, a schematic representation how the inside actually looks. So everything which is inside this small cube design, which is 1 cubic centimeter. We have the laser diodes, we have a lens system, and please don't forget, this is only a schematic representation. The actual uh, the actual lens system is way more complicated to fit it into this very small size. And then we have also a schematic representation of an actual mirror. This is a 2D MEMS mirror, a two-dimensional MEMS mirror. And actually this 2D MEMS mirror then does the creation of the image by doing some nice scanning of the laser. This is actually also what I would like to show briefly. So in the end, we see a lot that, especially on the AI, on the artificial intelligence, there are a lot of players in the market who are doing a lot of good things now, starting with OpenAI, but also Google Gemini, a lot of different things there. But what is missing is actually is a user interface, because you don't want to have all the thing by voice commands or also voice recognition. You don't want to do this. You also want to see something where you can actually see something, so you can see uh, what is happening, what the artificial intelligence did. And this is what we really see as the key driver for augmented reality glasses. We do see hands-free uh, um, transcriptions, actually, so online live transcriptions. We see lifestyle that actually you have a camera beside this projection system, that you can also take the pictures and also do some stuff there, and also productivity. And now, what are the things that you can really do with such a very small uh, projection device? As mentioned already, consumer market, this is something where we are coming from, which is very nice actually. What we also see where we can use it, and I'm going to show you next slide, more application details, you can also use it for in the automotive market for different applications. And last but not least, you could also use it for the enhanced optics market, where you actually have then something projected into the sights, something which is then really helping, for example, on a golf pathfinder or on other stuff there. And why can we do this? Because we really have something which for all kind of markets is very important because we use this laser beam scanning uh, solution. We have the smallest volume that it's necessary for the application. We've got the highest uh, image quality. We have the optimized power consumption because especially for the classes and also for some other stuff, it is very important actually to have the uh, to consume to minimize the potential power which is used to do this. And last but not least, we have a very scalable production. Then let me go and show you what we actually see in the automotive use cases. In the automotive use cases, we see on the left-hand side, we see something which is called window projection. There's actually the mantra behind this one is that any surface that you see, also the window itself, for example, the side mirror, the side windows on the back side can also become a display. What can you do there? You can actually see, for example, the charging status of your car when it's an electrical vehicle, when it's charged. You could also see potentially, if you're a big soccer fan, you could see your favorite team, what the result they played the last time or actually playing now. Or also, for example, if you're using an Uber or a different kind of taxi system, that you can actually see, okay, this is now my cab, my Uber to enter, and this is what you can see. So a lot of different use cases. And this whole thing is enabled by our small size projecting systems, because you don't want to have a huge package somewhere installed in the ceiling of your car, but you want to have it very small. The same thing is also for the heads-up display, HUD market. There we see that with our technology, we can actually go ahead and do a lot of different use cases, especially which has become very popular is this pillar to pillar. So from one side of the windscreen to the other side of the windscreen, where you can have a lot of different kind of information displayed. Uh, this is very uh, interesting. You can see not only what are the lanes doing in front of you, is there a car in front of you, and also the other stuff there. And last but not least, also what we call as ground projection, where we actually project something onto the ground. For example, it could be, when the pedestrians know, hey, this car is reversing, but you could also have what is called a welcome carpet, where you actually show uh, what is actually that is your car, also the electrical vehicle charging status. So I said a lot of different use cases. And let me go back a little bit on the technical data and specifications. So this is, as I mentioned, this is called the Trixel 3 laser beam scanner. This is the heart of our technology. This is where the actual light comes out. And what kind of specification does it have? The volume, as I said, around 1 cubic centimeter. The weight, less than 1.5 grams, which is also quite nice because you want to have it very lightweight. The field of view, which actually means how large is the image then inside, for example, the waveguide that you can see, it's more than 30 degrees. What is the resolution? The resolution is 800 by 600 pixels at this point in time. This is also something where we, with laser beam scanning technology, see a clear way forward actually with laser beam scanning, where other technologies, especially on the full color side, will have difficulties to increase it by a lot. Then refresh rate, we can go up to 90 hertz here. We are only using one 2D mirror, which also means we keep the costs on an acceptable level. From the brightness, or I should call it the luminous flux output, which actually means how much light is coming out of this cube. This is around or less than 15 lumen if it's uncorrected. The brightness or the perceived brightness with a waveguide depends a lot on the waveguide itself. So this is then something which has to be taken into account, but also with different waveguides, 600 nits is something actually what we see here. Power consumption, uh, this is 145 milliwatt for one cube. So if you have a binocular system, you would need to have two of those devices, one on each side, that each couples into the waveguide for the glasses. But this is also uh, a very good value. Then what we also have here is the color gamut, as mentioned. we are using this laser system, so this 240% of the sRGB space is really, really large. And last but not least, also the contrast. The contrast with our technology is very high, and the reason for this is actually that we can switch off the laser exactly at the moment when we don't need to have anything to display. So black is really black. We call it, this is a true black technology because we switch off the laser. Of course, this actually means that in order to make this happen, we need to have a very good control of the lasers. So we need to switch them on and also off very fast. And for this one, actually, as I mentioned, we needed to shift a lot of the complexity from the hardware domain to the software domain. And let's get it started actually. On the left-hand side, we're using something which is called laser shoe scanning. I have also something on the next slide then, how this compares with other technologies which are out there on the market. We're using our software expertise for the device, for the device control actually. What you can see here is without what we call the trajectory control module, all three colors would hit the screen somewhere different. So even though it might look quite funky to have the three colors separated, this is not what you can make nice pictures with. And this is why we actually have this the trajectory control module integrated into software, that we can actually have a real white where we have it, and as said, also a true black where we don't want to have any color displayed. And last but not least, not so important for the user, but for us, for our manufacturing, also our calibration system are based on what we call a software-defined display. And then let's maybe stay one more time with the laser shoe scanning. As I said, in the end, this laser shoe scanning is something which is a little bit different to what people are normally used to. So normally you would have a rasterized scan, so which means that you would have one line which you do, that you finish, then you would have the next line that you do and finish. And this actually uh, would also work for our displays. Uh, but we see that especially to get the performance, and the performance, I mean the high resolution, the good image control over varying temperature, we need to go to laser shoe scanning, because in the laser shoe scanning, as you can see here, uh, you can actually see uh, that you have sort of sinusoidal waves, which always have an endpoint and a begin point. And with this one, you're also able to fill the screen very fast. And these are the key things. So in the end, from the usages of the laser, so in the end, how long can we have the laser on to get the full white and that kind of stuff, we see that laser shoe scanning has really a big improvement, because otherwise, if you have a rasterized scanning, if you at the last line, you have to go back to the first line, and for the first line, you need to switch off the lasers. And then, of course, until the time you are at the top left again, you actually have to, there's no laser power that you can use. With laser shoe scanning, everything is much faster, everything is much more compact. So in the end, you can actually go ahead and do a lot of uh, stuff in software that with a rasterized scanner we simply do not see. And last but not least, we also see that, especially from the performance with regards to stability over temperature, these are shoe scanning where both axes, I mean, as I mentioned at the beginning, this is a 2D MEMS, so a two-dimensional MEMS, so it flips in two dimensions, it can be moved in two dimensions. There is also a big advantage that both of the axes can be sort of in at the eigenfrequencies, which actually means that uh, they are very stable with regards to their movements. And this stabilization is very important if you can think of what I told you before, which is, for example, the automotive applications. So there you have temperature effects coming in. You have to work in minus degrees, you have to work in plus degrees Celsius, which actually means that you need to have a very stable system. And as I said, we've got the combination, we've got a very good hardware, but also we have shifted a lot of our stuff into the software domain. What we also have, and this is also what I would like to uh, mention here, is actually that we also have a lot of good supply chain partners. So in the end, what you can see here, we're having here Infineon and DDK. So these are one of our key partners for certain components, and these certain components, especially on the optical side, where we actually work together with them to bring out also new versions of their MEMS mirrors that they are doing. So this is also something which is very nice. On the other hand, we are working with a complete ecosystem, and the complete ecosystem includes that we're working, for example, with waveguide manufacturers. Waveguide manufacturers, a short explanation, actually, this is something where the light is coupled into the glasses, sort of, and then coupled uh, into your eye, because we don't write directly from our LBS system onto the retina, onto the eye. We project something on in the glasses, and for this one, we need to have certain ways of actually transporting the light that is in front of you, uh, and this is done on what is called a waveguide. So there we have our partners like Cellit, like Optiax, like Dispelix, and of course we have other partners there. Last but not least, we also have a lot of uh, different options to go ahead with our assembly, because also we are doing a lot of our uh, assembly and manufacturing with our partners, and there, as mentioned, for the automotive versions, we also need to have qualified automotive assembly locations from our partners, and this is what we're also having. So in the end, it's not that we can do it on ourselves, but we really need to have our technology, our key partners available. And this is actually just a quick thing that we also have our management team there. Our management team, I would like to only mention Dr. Jörg Reiterer. He has been in this LBS area and this expertise of more than 10 years. So he has won way more than 50 scientific awards. He has won the Photonics 100 award two consecutive years. So he's really known in the industry as one of the key technology and expertise leaders for laser beam scanning. And with this one, I actually would go to a slide where I also would like to show the complete team and thank the complete team for working on it. And also, as it is mentioned here, uh, the whole thing of creating a very, very small uh, laser beam scanner is not something that only one person can do, or not only one team can do. It takes a lot of different teams to make it work, because we have the optical part of the equation, where you actually need to make sure that uh, you have the right beam path, you have the right components, you can do everything that is actually in a way that the light comes out where it should be, in the quality that it comes out that it should be. A lot is done on the electronic side. As mentioned, we need to have the laser driven with very short pulses to make sure that we create the right image, to have a very high refresh rate, and also have a lot of control there in this trajectory control module. And last but not least, also on the mechanical side, to make really such a small uh, laser beam scanner. This is also something where we need to have very good know-how. And this is actually a representation of the team. As you can see, we are not a big company, but a rather small scale-up company. But what you can also see, we're located in the heart of Europe, which is Vienna. So this is actually quite close to our office, which is one of the more famous churches in Austria. And with this one, I don't just say this is where we are located. We do have in Asia and in America existing and also planned support, but our headquarter and our key offices are located in Austria. And with this one, I think most likely I can hand over to questions.
Thank you very much for the informational and valuable presentation, Dr. Nikolai. So let's see if there's any question from the floor.